Hi, we're Group 68. The goal of our project is to predict the popularity of Spotify tracks based on their musical attributes such as danceability, energy, and loudness, as well as their metadata such as artist, genre, and release date. Popularity is measured using Spotify's popularity index, which ranges from 0 to 100. The research question is therefore how accurately can a model predict a track's popularity using its musical and metadata features?
During initial data cleaning and EDA, we excluded a few observations with missing entries and classified the input into 11 categorical features, 11 numerical features, and one response variable. In addition, we applied standardization to all numerical features, and when visualizing their distributions, we observed a diversity in distribution shapes, including symmetric, skewed, and sharply peaked distributions. A correlation heat map also highlighted mild multicollinearity in a small subset of features, influencing our choice to explore feature selection prior to model development. Next, we explored trends in track popularity for categorical features. Genre-based box plots illustrated that popularity distributions differed somewhat across genres, but a strong variability across subgenres indicated that other characteristics also contributed to popularity differences. Lastly, our response variable showed significant skewness, with many tracks clustered at very low popularity levels. This imbalance informed our decision that assuming a linear relationship between features and response might not be appropriate, thus motivating more advanced models.
Given that our response variable track popularity is continuous, we began with linear regression as our baseline model. The baseline resulted in a mean square error of about 520 and an R-square of 0.16. This result suggests that the relationship between features and the target variables are likely nonlinear, making linear regression insufficient for this task. Feature importance analysis reveals that categorical features, specifically those related to subgenre, dominate. This indicates strong associations between music categorization and listener engagement, emphasizing the role of metadata in predicting popularity. Given these findings, we opted for nonlinear tree-based models like random forest and gradient boosting, which are better in capturing complex relationships and feature interactions. This approach allows us to dive deeper into understanding the factors driving track popularity. In our training process, we used randomizer CV to tune the hybrid parameters for each model. We tested 50 random combinations of hybrid parameters for each model with threefold cross-validation to ensure robustness. The tuning process used negative mean square error as a scoring metric to identify the best performing combination. After tuning, the best model for each algorithm, random forest, XGBoost, and LightGBM, was evaluated on the test site. We compared the models based on their R-square values to assess the goodness of fit, and results showed that XGBoost outperforms other models with 0.29 R-square.
Now let's talk about what makes a track popular based on our analysis. Numerical features like energy, loudness, and duration emerge as the strongest predictor of popularity. These features capture a track's composition and emotionally connect with listeners. Metadata features, such as subgenres, provide valuable context but play a secondary role compared to musical attributes. From the bottom right plot, we can also see that linear regression over-relied on subgenres features. This highlights the importance of using LightGBM to fully capture the nonlinear patterns, such as how danceability and occultness interact with other features to influence popularity. To better understand these contributions, we use SHAP analysis to interpret the LightGBM model. SHAP helps us identify not just what features were important, but how they influence predictions. For example, higher value of energy and tempo consistently increase popularity, as seen in their positive SHAP values. Meanwhile, numerical features like instrumentalness and loudness also show a strong positive impact. On the other hand, metadata like subgenres contributed less but provide complementary insights, with their influence varying across tracks and listener demographics. So what does this mean for the music industry? For artists and producers, focusing on optimizing musical attributes like energy and instrumentalness can significantly enhance a track's appeal. Streaming platforms, on the other hand, can leverage metadata like subgenres for personalized playlist curation and targeted marketing strategies. In short, by combining the power of musical and metadata features, we provide a scalable and accurate solution for artists, producers, and streaming platforms to better navigate the ever-evolving music landscape.
We can improve our project through data augmentation by integrating external data sets such as music reviews or social media metrics. Also, we can include more complex feature engineering to incorporate metadata like regional popularity trends or collaboration networks. Temporal analysis using time series models is another potential modeling approach that can also capture seasonal and dynamic patterns in track popularity. Finally, expanding our dataset through additional data scraping using the Spotify API will help us to train more robust models. Thank you.